Good afternoon, everyone. My name's Ashley Aitken, and this morning we saw some cool technology and some cool discussions from Nigel. This afternoon I want to introduce you to, I think, is a really cool architecture for enterprise systems. So I'm really excited about this, just as much as Mars and just as much as the VR and so forth. But to start with, this talk is CQRS and event sourcing for the win. My name is Ashley Aitken, as I mentioned, from Innovately. I think this is a really interesting architecture, but an important architecture. And I think that even if you start off with a different architecture for your enterprise systems, you actually end up getting something like this by doing all the things necessary to make it to succeed. So why not start off with something like this anyway? Just for giving you an idea here of what the audience is like, who's heard of CQRS and event sourcing? Okay. Who's used it? Okay, quite a few. All right. That helps me out with the audience there. I presented a similar talk before on this, but I got through only the first half or so I'm focusing on the second half in this one. But I'm also going to run through the first half quite quickly just to bring people up to speed if they haven't heard much about this and to give you the context. It can be quite a complex architecture, but I'm trying to actually get to the core essence of it, and I don't think it's too hard, really. So the topics, the introduction, the overview, we'll look at what is CQRS, CQRS and event sourcing. Then we'll look at the final section, which I think is really cool, about persisting application state. For many years, the relational database has been the core of our persistence because of the many reasons I'll talk about. Of course, NoSQL has come along and questioned things there, but I think maybe we have an even better solution for persistence. So, this is me, a computer scientist. I work in professional training, academic, and software development. I'm principal at Running Code Productions, which sort of helps out with enterprise applications. But these days I'm also focusing on innovation, innovately.com. I focus on applying lean startup techniques and principles to enterprises. So helping companies innovate by using these techniques that startups use. Very interesting stuff. And also I'm more on the Java side of things rather than the .NET and Scala, as you see there. So a little bit, what is command query responsibility segregation, and where does it come from, and what problem is it solving, I guess you should ask. Well, if you have a look at a traditional N-tier architecture, something like this, we have the presentation layers and the business layer, which is often in the OO sort of application, and a proxy up the top, and we have the relational database down the bottom. And this scales in many ways. You can have lots of many presentation layer instances here, and many backends working with relational database. But there are problems, and one of the problems is it's difficult to scale this relational database. We can do sharding, we can do mirroring, but it's all complex, and you get issues with transactions and so on. So there's a problem there which held us back and made it difficult to scale. Other problems with this approach was it's pretty unbalanced. If we think about it, most of our application usually is read side. We're querying the application to find information with enterprise applications, with large applications. Not so much writing or changing things, but really there's one stack just for everything. So it's really not meeting the needs of both of these sides differently. I mentioned it's difficult to scale because of the relational database, and we may need different stores for our different models. What if you want to have a graph database to store your graph stuff, and a relational database and a document database? How do you manage those on the back end? And how do you handle transactions across those multiple data stores? Some of the possible solutions we have these days are things like two-phase commit and three-phase commit and distributed atomic transactions, and they get very complex and very difficult and slow and can't really scale to meet our demands of enterprise applications and consumer applications in the 21st century. So this is why CQRS came along. How can we solve these problems where our traditional architecture doesn't able to cope with the scaling needs of our current business demands? So if the root of the CQRS approach goes back to object orientation, and I'm not sure Bertrand Meyer was thinking of architecture when he talked about this, but when we used to do objects and classes, we said, well, objects should have these things called properties, which give you some information about the object, and they should have operations, which change something in the object. But you shouldn't sort of mix these things. You should keep them separate. This was a good object-oriented design principle that I taught for many, many years. And this principle now we're going to transform and apply it to our architecture of our systems, our enterprise systems, and see what it does. So again, here in a simplified form is our traditional N-tier architecture with the presentation layer, the business layer, and the persistence layer, which I'm sure you're all familiar with. So what does CQRS suggest we should do? Well, basically it says we suggest split out these two parts, the write side and the read side. So now we have one stack over here for changing our database or changing our persistence, and one stack over here for reading from that database. I've actually kept the two levels here because we may want to scale the front end different than the back end in terms of number of instances and nodes. But we have these two streams now. Basically, we think of these as the command and the query stream. On the left-hand side for the writes, we have commands. These commands come in and tell the write side to change something in our business model, in our persistent store. And we have the other side, the query side, which says, hey, we want to find out something about our enterprise application to display on a page and a web page and so forth. So we query on this side. So two distinct stacks separate from each other. At the moment, they're sharing the same relational database store, but we'll see how that can change in a minute. Because we have these two separate stacks, we can also now have two separate models. And I mean models here with how we represent this in our business application, object-oriented model, or whatever you wish to use. So of course, on the command side here, we would build a command model, a model of our business or our objects and so forth, which is what we want to do, apply these commands to. It's focused on changing the model. But on this side here, in the query side, we can have a different model. That query model now is not about changing the objects in the business model, it's just about reading it. So maybe it can be a simpler model, not so much business logic, not so much complexity. That's called the query or the read side model. And again, two separate stacks. So if you think about it in terms of the object approach, but also now in terms of our enterprise architecture, what sort of commands can you have? And the typical banking application here, you have a deposit money command, or a withdraw money command, or an add interest command, or a change owner command. These are things to change our banking model. On the query side, you'll be getting balance to display the balance on the page, or getting the owner, or getting a transaction list, or getting the accounts. These are, again, just read side things. So here commands, and here we have queries. But notice how they're very similar to what you may have in an object-oriented model of a bank account or something like that. Now, the commands here are sort of the natural ones for bank accounts. But often with enterprise applications, we think in terms of CRUD type stuff. Let's have a create address command. Let's have an update address command or a delete address command. Of course, retrieve would not be a command, that would be a query. But one thing we do suggest in CQRS is you get away from this sort of CRUD thinking and start to think about task-based commands. This is what actually the task or the intent that the user has when they're trying to run this command. What are they trying to do? So for example, we may have normally update address as an update part of a CRUD approach. But really, what's the intent of the user there? Are they fixing an error in the address? Are they actually moving to a new address or changing it to a primary address? You can capture there some intent about the command rather than the fact that it's just changing the data. And that can be very valuable for you in your application later on and in the CQRS approach. So it's not explicitly a part of CQRS, but I recommend looking at task-based commands. So how do we scale this approach? Well, it's nice now, because we have these separate parts, we can scale them independently. So the write side, maybe not so much, but the read side, where we see lots and lots of action, we can scale much more, many more instances to handle the load. Separate scaling, we've solved that issue of not having a balanced style architecture. But again, still, there's a problem with our relational database. We have this persistence bottleneck, which we can't scale that easily. And in terms of OO too, you've probably heard many times we have the impedance mismatch. Getting our objects from our relational database can be difficult. We use Hibernate or other systems and they're complex and heavy, and you want to actually just deposit some money in the bank account. You have to go to the database, get your whole object, reconstruct the object, maybe related objects that are connected to it, build the whole object, and all you do is depositing $10. No complex business logic, just a simple deposit. But you had to do all of this creating the object here and building a complex model just to do something simple. And similarly on the query side, here you may have a different model, I suggest, which is simpler. So you can change the model to match what is needed. So there's this bottleneck in the persistence still. So we've made some progress. We're scaling our reads and writes as necessary, but still the problem with the relational database. So again, going quite quickly here, I hope that's okay. People following okay? Yep. We're doing well. So the second part of the story is adding in this idea of event sourcing. And it sounds quite complex and difficult, but it's just a different way of persisting your information, your state, and we'll explain this. One way you may understand it better is if you think of a simple example, making an application for purchasing concert tickets. So your simple object model or data model would be we have a concept entity, which has the details about the concert and the price. We have a ticket entity, which is the buyer details and the ticket number. And of course, a concert can have many tickets. So how do we use this in our application? Well, we build up a concert with a certain price and certain details. We sell some tickets and we save them to the ticket store, the database, or so forth. And we're going fine. But then suddenly we have to discount the price of the concert because we're not getting enough sales. So we discount the price of the concert by changing this. And now we've lost some information. Because we had those customers who bought tickets already, they paid the full price. We've changed the price here, so now we no longer know what price they've paid. And similarly, if customers buy some tickets and then cancel those tickets and we delete the records, we lose the information about those purchases and cancellation of tickets. So in our traditional data model, where we represent the data as a model in our persistence at its current state, we're actually losing a lot of data. Every day we're losing information that we had, but we just threw away because we overwrote it in our database or in our store. We're losing data. So how do we handle this? How can we maintain this extra information, which can be very useful for the business? What can we do? If we look at other similar solutions to similar problems, for example, in accounting systems, they don't just keep the final balance of the account. They keep all the debits and credits along the way. And they work out the final balance when they need to, or keep it as a sort of temporary state. They maintain the transactions to record all the details. Similarly, in how file systems work these days and databases work these days, they use a write-ahead log to basically log everything that's done, basically, for reasons that they're more reliable and robust if they have crashes, but they're keeping all this information in a write-ahead log. And similarly, if you look inside databases, and particularly database replication, they use this same sort of approach. They're going to send update events, which record everything that happens in the system, rather than just the current state of the database. So CQRS, with event sourcing, tries to follow this lead and says, rather than just keeping the state, let's track the changes to that state, or events that happen. So rather than just having our events which come in, the commands, come in and change the state, our commands are going to produce events. So we bought a ticket at this price event, so we changed the price of the concert event, or someone cancelled their tickets events. We're going to remember every bit of information in some sort of event log. We store these events, not the domain state. And I'll show you soon how we can rebuild the domain state, but we store these events, not the state. When we get our command, we update the domain state from the events as needed, but most importantly, we don't update the domain state until we've persisted that event. Because once we've persisted the event, now we know even if we lose all our domain state, we can rebuild our system from all of these events. So we save the event first, and then we can change our business state. And later on, if we want to actually rebuild our business state, we've got rid of our memory representation of our data model, we can go through these events again and rebuild the state, just like you went through the debits and credits in an account to find the balance. So we can very easily rebuild the state from the events. So this is event sourcing, saving the events that happen, not just the state of your application. So characteristics of events, they're immutable. They never change. When you create an event, something happened, it doesn't change. It's a piece of history. They are stored in append-only storage. You never need to update an event because it's immutable. And you can replay events, as I mentioned. We use them in event sourcing to rebuild a domain state and save our domain state. But events can also be used, and I'll show you later on, for managing processes inside our applications, signaling process states, and integration between subsystems in our application. So events are very useful to use these days, and more applications are becoming event-driven. So this event sourcing fits in well with that. It also gives us the chance to audit things and allows us to do analytics, because we've got a whole sequence of events we can analyze in our system, rather than separately creating logs and building event streams. So this is the general approach, and how does it apply to our concert tickets example? Well, rather than just directly saving the state, whenever a command comes in, we would create these events, like the concert created, a ticket was ordered, the price was changed, another ticket was ordered. And using this state, we can look back in our history and see when a ticket was bought and what price it was bought at before the price changed and so forth. We're preserving all of our information, which is very valuable to do. So the essence, of course, is commands produce events. Commands come into our application, we check the command, we produce the event, and it saves somewhere in something like an event store, just a storage facility for events. And again, this is a write-ahead log, so you just write them there, you don't actually change them in there. It's an append-only storage system. But that's the general structure. So what's the difference, again, between these commands and events? I mentioned commands are task-based, so focus on what task is the command trying to do, its intent. Commands are asking you to do something. They're often written in an active verb, like do this or change this. Commands can be rejected. So a command comes in asking us to withdraw $1 million from our bank account. Oops, sorry, you don't have $1 million in your bank account. That command is rejected. So not all commands are actually processed. Can be responded to and they can be lost. If you lose a command in the process, it's not so bad, you can try it again. Okay, so it's okay to live with commands that don't get processed and are lost. On the other side, events. Well, events are for things that have happened. They're facts, as I mentioned, immutable. So they never change, they never need to be changed. They're often written in the past tense. And I mentioned they're append only, and there's no derived information from them that the events are the information. And they cannot fail because there's something that's happened. Okay, you've written it to the event store, it's happened, there's no chance of being rejected. It's at most post hoc an event. So that's commands and events. Here's back to that bank account example. Here's showing you how they would look in the bank accounts. Deposit money could be the command. And then the corresponding event in which you would write would be money deposited. Okay, so this is saying it happened. And we've changed our business data. It's up to date. Withdraw money, money withdrawn. Add interest, interest added. Set account details set. So there's nice correspondence between the commands and the events that record those commands when they're successfully operated. But how does it actually work in the application? What's the sort of logic we follow through? So if you look in more detail inside the application, we have a number of steps. So the command comes in firstly, and the first thing you do is check the command syntax. Is all the right data there in the command? And this is a superficial check. It doesn't require any business logic. It's just checking that everything's okay there. If it is, then we're okay to keep on proceeding. The second step there is to validate the command with business logic. So now we need some business logic to actually say, is this an appropriate command to actually process? Can we process that? Now, a lot of commands are just changing things. There isn't limiting business logic. So in the majority of the cases, you can just go ahead and do the command. No need to worry. But in the example I mentioned, withdrawing $1 million from a bank account, you would have to construct your business state here to find out what is the balance of the bank account before I can either accept this command and do it or not. So if it was $1 million in my bank account, I could proceed. If there wasn't, I would reject this command. So you're only building up your object state or your business state as you need it to validate the command. It's not building up everything. You just need to do what you need to do. If we do validate the command's business logic, then we move on to the next step. And the next step is now write that event to our persistent store. We've approved it. We're going to do it now. And once that's written, it's basically gospel. It's done. Okay? So we can't change things. But of course, writing the event to the event store hasn't updated our business model. So now we have a chance to update our domain state in here to change the bank account balance if we want to and want to keep it in memory. So these are the sort of steps you go through when you're processing a command and producing events. If everything crashed here, no worries. We can come back here and read these events again, as I'll show you in a second, and reproduce that state. So once we've written this event, we're safe. This is our persistence mechanism now, not our relational database type store. So I mentioned then rebuilding the state, so the saving here is most important. If we do want to rebuild the state of our business, how do we do that? Well, we just go through and read out the events related to this particular bank account or this particular concert. Read through the events and process those events to find the final state, the current state. Now, people often ask about this, aren't there a lot of events to go through and so forth? But if you think about one particular bank account, there's usually not that many. And also there's a mechanism associated with CQRS called snapshotting, where if you have a lot of events, you can make a snapshot of the state, which is sort of like a summary. You don't delete the previous events, but now you have a summary where you can start off rather than going right back to the first event. But this is actually quite efficient and quite fast and not difficult to do. So we want to rebuild our business state to do something with it, to apply some complex logic. We can actually read the events and rebuild those and then update the domain state. So this, that works, yes. So this is basically the CQRS architecture. So I say 2 streams, 2 stacks, one the query side, one the read side. We produce commands over here, you give us events, an event store, and we have the query side over this side. Now really it's not an architecture, it's an architectural pattern. So you shouldn't think of it as being the architecture for your whole application. It's more a part of your application which encourages collaboration, which needs this sort of scaling, may use this approach if you think it's appropriate. So it's an architectural pattern. But I want to break the pattern down again, just to show you a bit more of how it actually works and what different parts relate to each other. So the first step we saw was processing commands on the right side. So this is the part of the stack that does that. Basically, the commands come in, we validate the commands, and then we write them to the event store and update our state if necessary. So whenever you're making a change to your business, on this side, this is the part of the applications that used. The other side doesn't even really come into it. So it's a bit different than traditional applications, because when you put a request in here, you're sending through this command, what do you get back? You don't get back an answer saying, here's the final balance, or here's the new state. You just get back an answer saying, yes, we've received your command, and it's validated. Or maybe not even that. So it's a bit of a different architecture here. You're not getting back the next state of your web application, or the next state of your page. We'll talk more about this a bit later on. But this is the process commands on the right side approach. Commands in, generate events, save them in the event store. So how do we get this other side of our application, the read side, updated? Well, there's a separate part here, which is sort of like responsible for taking our events and updating our read side. So we have all our events which have been put into the event store. We have an event handler here which is listening for these events. And when the events get into there, it's sort of notified, it takes the event and it updates our read store. This is very independent and separate from the right side. So there's some application code here running which is listening to this and updating this when it can. Not instantaneously, just when it can, when it gets around to it. And we'll mention that a bit later on. So that's the second step. And the third part of the architecture is just this query side. And as you can see, the query side is much simpler now because it's just reading information. So a query comes in, this front end handles it, and basically goes to the database and gets the information and returns it. So there's no complex operations or building object models. It's just getting the data and returning it. You can have more complex models, but in the simplest way, we can do this. The benefit of this is we can have multiple view stores. So now when your application needs to scale and you want to actually be fast to provide back this information, you can create a view store just for the information you need for these particular queries. Because remember, you'll have something on the back end here which can update any particular view store you make. So you can have multiple view stores providing responses to particular queries. And even better, you can add view stores at a later stage. So maybe you're going on, you see, oh, it's getting very slow, my queries are too slow, I need a graph database. You can add an extra graph database in here, I think a bit later on that slide, a graph database in here, and fill that graph database up based upon the events you have stored to now quickly respond to queries that would use a graph database better to respond than a traditional database. So having multiple view stores allow you to match the queries to your view stores to make the read side very efficient and very powerful. So that's the third step. So the important thing here is, again, separating these commands on the right side from the queries on the read side. When we do the commands, we only need to rebuild the application state necessary to validate that business logic. We don't actually keep the application state all made. We don't need to, only the stuff we actually need for particular commands. And on the query side, we only rebuild the application state enough to do some business logic for the read and return the data. But we can even make sure the query model doesn't even need any business logic. It just returns the data for the query. So this is most important, this separation here. As I mentioned, the query side, we can have different data stores. So basically, we have SQL, a standard one. We can have a graph database or a document database. And we can update these as needed, so they match the queries. And we can do denormalization. So if you have a complex user interface which needs lots of different objects, rather than having to build all these objects up and make sure you can query them, you actually denormalize the database, produce a new store which exactly matches your query, and now it's very quick to respond to, which is what we do often with caching and so forth. A caching store is basically that. It's a cache of these complex build-up responses to queries, and we cache them. We can think of these as like a permanent cache, which is made for just what we need to do. So again, this is a most important part. The view side, the queries, can be tailored to what you need in your application to scale well. So again, here's the CQRS subsystem. Here's our different databases. We have a graph database now and a relational database. So now when the events come through, they update both of these data stores as necessary. We write the code to update these based upon what events happen, and they will mimic what we need. Query comes in, we can get both from there. We have the stream handler to update this one, and we have the process to update the other one. So we're event handler is updating both. So this is the general architecture, and I hope that gives you a quick feel for what it's like, being very quick there. Just to show you a couple of further power things you can do in the architecture, this is another diagram which tries to represent the architecture. Up here you've got the command side going through here. So again, you'll get your command handlers here to validate the commands. You build up your domain model. You're storing your events here. Here you have an event bus. So the events can actually respond and you can make changes in your domain. We'll see that in a second. On the query side here, when the events come across, we can update our data stores. So now we query here with a thin layer our data stores. But you may also have analysis databases there, where all your events are producing analytics. These days we're into big data and analytics. We can have live updating of our analytics there, because the events can be used to manipulate the analytics views. And similarly things here like sending an email. When an event comes out, you can send an email out, a different form of response to event on the query side. So it can get quite complex and powerful, this sort of architecture. The interesting thing and the more complex thing about this is we have the notion of eventual consistency. Because the write side is separate from the read side, it takes a little while for these events to trickle across to the read side and for the read side to be updated. So the read side may not instantaneously represent the value you have in your business data. Is this a problem? Well, possibly not, because once you read something from a database, it's instantaneously out of date anyway, unless you've locked the database. Something could have changed the data behind you. So it's a matter of degrees here. And we're sort of admitting that data is always somewhat stale. It's always going to take a while, or will always eventually be consistent. So eventually consistency can take a problem. It requires a change in thinking, how you approach things, thinking about transactions, thinking about user interfaces. And you can see the differences in a couple of examples. Traditional web flow, you submit a form to an application. Here comes my data. And your response gets back the results. The new state of the application responding to that data. Person submitted a deposit in a bank account. You get your new data back. It's the balance of that bank account. With CQRS, you can't do that. You submit a command request, and you just get the command result. Was it okay? Yes, that command was okay. To actually find out the balance of the bank account, you actually have to submit a query and get the data back. And if you submit the query exactly the same time or just after you submit the command, the result you get back may be the old balance, because the data hasn't trickled across to the new side yet. So you have to start thinking about this and how we handle our user interfaces and what we display and what we expect to see. You may see a lot of new interfaces these days. They have a little spinning wheel for a while, or they pop up a dialog box to give the interface a second to get the data refresh on the read side to produce the updated data. But this generally isn't a problem. So options we have here, we can wait until the read side updates. The client can poll the read side to see whether it's been updated. We can signal the read side to tell it when it's updated. So it just waits around until it gets the signal. Or we can fake the client. So the client pretends like it went through okay. It guesses what the interface would look like. We fake it until we find out something's wrong and we correct it. So there are some options there to handle this eventual consistency. There are a couple of interesting case studies of this, which I'll just briefly touch on, because I've got a lot to go through still. This one is when you set up an account, you're registering here. So you'll come onto your user interface, you're typing in, choosing a username, and submitting that username. So when we actually find out, we type in that username and we submit it, in the time since we've submitted it, someone may actually create that username. So our command may not be validated. So how do we handle that? Well, we can try and handle the situation where someone chose an exact same username as someone exactly a couple of microseconds before them chose a username, which is what you may have to do. But generally speaking, it would be easier just to flag it as a problem and fix it up, because it would be so incidental and so rare for this to happen. But that could happen with the CQRS eventual consistency. Another example here is when you go into a cafe. And this shows the approach to transactions in eventual consistency as well. You may be ordering a coffee from the cashier. So you go in here and you basically submit your command to the cashier to order a coffee, and you get a receipt back saying your coffee's ordered. And you go and sit down. But you don't know what's going to happen in the back here. When the cashier talks to the barista, they may say, oh, we've run out of that coffee. You can't do that order. Now, if it was a complete transaction, we would have ensured that all can happen at the same time. But in the real world, we don't have that problem. We have that problem, but we don't actually try to solve it with transactions. We don't check everything before we do the command. In the real world, the cashier would come back to you and say, hey, we haven't got those coffee, would you like one of these? And you say, sure, that's fine, I'll go ahead with that. So you'd make some adjustments afterwards. So this is the way CQRS operates, not trying to have a huge transaction, but handling these problems, which may be rare, but handling them in a way which is not transaction-oriented. So humans do this. We live in a world which is eventually consistent. We find out later that there wasn't a thought of coffee rather than at the time of purchase. And we tend to get along okay, so maybe we should make systems more like this, or we can make systems more like this, rather than to make them totally consistent. So a couple of bits of further look at events inside CQRS. I mentioned events are very important, very useful. Events can be used for this event sourcing I've talked about, but also process management and communication and integration between subsystems. The way we handle processes in CQRS is having what's called Sagas, or process managers. These are basically a different type of thing. We've seen so far we have these command handlers in CQRS. A command handler takes a command, validates it, produces an event. Process managers or Sagas are a bit different. They basically respond to events and produce commands. So a process manager is listening for an event and produces a command which will affect the system. And using this approach, you can actually handle processes or have complex processes in your system. I'll skip over this. But this shows us an example here of our process manager. We place an order and we get back an order confirmed response. Then when this actually processes this order, it sends a command out to this particular order aggregate. The order aggregate produces an event which comes back. The event is recognized, and now the process manager produces another command. And then it produces an event. Our reservation was, seats were reserved. Once we've got that event, we can start to do another processing. So the process manager is basically sending commands, listening for events, responding to those, sending commands. So it allows us to coordinate complex processes using these events and using these commands. So that's the idea here. Sagas, they listen for events and produce commands. As I mentioned, this is also useful for subsystem integration. So if you have multiple subsystems in your application, how can you handle those? Here's our split between our two subsystems. So this subsystem over here is producing commands, receiving commands, producing events, doing its business. Our other subsystem over here can have a Saga, which is used for integration in this case, which is listening for events. And when it hears one of those events, it can send a command into its subsystem. So now we can integrate our different subsystems, not using API calls, but by event-driven. So the whole system now becomes event-driven, but it's still separated. The only interface is through these events. So that's another use for Sagas or process managers. And I'll skip over that there. I'll skip over this. Already running too late here. So pros and cons of CQRS approach. Well, it's very scalable. It's very simple to scale. It's made to scale. It's very cost effective with cloud deployment because each of these things can be scaled separately. We're not scaling one big application. We can scale the read side separately from the write side. We can rapidly adapt to changing business requirements. We can change our commands. We can change the events very easily, so rapidly adapt to those. The cons, or the difficult side of these things, are this eventual consistency. Takes a little while to get your mind around. Distributed systems can be a bit more complex, many applications rather than one big monolith application. And it does add some extra complexity to your application, handling these commands and events. I haven't got time to talk about event store, but this is basically a storage way to store events. And the one I use is Greg Young's event store. It's particularly made to store events and streams of events. What I'd like to finish off with in just the last 5 or 10 minutes is looking about this question of how to persist application state. So traditionally, we've persisted state by files, relational databases, and we tried object-oriented databases. That didn't work so well. They didn't take off. And why was that? Well, people said maybe relational databases are a more natural way of storing data, which is independent of our application's paradigm, whether it's object-oriented or functional or traditional procedural application. Relational is a sort of timeless way of storing data. And that was pretty true. That's why relational databases, I think, have stuck around longer than object-oriented databases. So the question I want to ask is, can event sourcing help us to store things in different ways? Well, with event sourcing, we know it enables us to build right models that are necessary to validate and perform the commands. So we can just focus on the needed model at the time we need it. We can build read models which match our queries. So the event store allows you to be much more flexible in which write models you have and which read models you have. Just like relational databases allow us to be more flexible in what paradigm you use, event sourcing allows you to be more flexible in what data stores you use and what models you use. So I think it's useful. But wait a sec, not all of our subsystems need CQRS. If you're building a big application, this subsystem may be complex, it needs CQRS. The preferences subsystem may be very simple, doesn't need CQRS. So how can you get the benefits of an event store, which is a sort of, I think, a multi-paradigm way of storing the data, when you don't need CQRS all the time? So I thought about this for a while, and I think there's a number of alternatives here, 4 different alternatives. Of course, if you're doing CQRS with event sourcing, then you have event sourcing and event stores, everything's okay. You're storing all your stuff in event stores, you get all the benefits. But sometimes we don't need all of these separate stores. We don't want to have this. We don't need this complexity of separate stores. So a simpler version of our subsystem could be, let's drop the separate stores. And let's just have a back end here, which creates one data model we use for the write route and also for the read route. One shared data model now. So it's simpler, doesn't scale as well, doesn't match our query sides, but maybe for some particular subsystems in your enterprise application, this would be good enough. What about even less than that? What about if we didn't actually even want to use event sourcing? We just wanted to have 2 separate sides. We're still keeping the CQRS separation. But we didn't want to use event sourcing. We wanted to store our data in a shared data store. Maybe a relational database here, maybe a graph database here. Well, we could still do that as long as we saved our events as well. So we still process our commands up here and save our events. We just don't use the events. We actually just respond in a normal way, a traditional application. And the same could be said with an application which didn't even use CQRS. We just have a traditional application with some data stores, no separate read and write sides. Maybe your subsystem doesn't need that separation. You can still keep this approach, have a command come in, save the event, but just operate traditionally once you've saved the event. I think if you do this approach for all your subsystems, make sure you store your events, you then have the flexibility to use the simpler models, but also to change between these models. So if we started off with this simpler application, we find, oh, we have to scale this subsystem now. Because we've stored all the events, we can go back to this one and say, okay, we want to have separate or different database stores now. We can rebuild them. If you find you need to scale more, you can go back to this one. And eventually you can go back to this. So as long as your architecture has the notion of commands in it and save the events once you're validated, it doesn't matter what you use in your subsystems. It can be CQRS, but it can be a lot simpler. You don't have to go the full way. So I think using an event store gives us the flexibility to change our architecture as we grow, as we scale. When you're building the application to start off with, you could just start with this approach, and later you could actually change it to one of the others. So the benefits here, you can change the architectural pattern if you need it, and when you need. You can use events for integration across the subsystems, event-driven systems, great. And we can use events for analytics, for data analysis, for real-time data analytics. So basically, I think lots of benefits of that approach. And in this approach, the event store becomes your core storage. Not a relational database anymore, it's the event store. This is why I think the event store can be the ultimate solution to persistence. Don't persist your state, but persist your events. We can use them for analytics, we can use them for constructing our data models, we can use them for integration, and we can change our architecture flexibly as we go along. So that was a lot there. Hopefully it was sensible and you could follow what was happening. In summary, I guess we've seen a number of things. We've seen that CQRS means separating the commands and the queries, the write models and the read models. We've seen that event sourcing means persisting events rather than domain state directly. It's a different way of doing persistence. We see that CQRS and ES result in eventual consistency, which may sound strange at the start, but you can get around it. It's livable, and it actually works more like the real world. And we see, lastly, that events may be the ultimate and most timeless way to persist our application state without actually persisting the state. We're persisting the events. And of course, we have lots of memory and lots of disk space to store all these events now, so there's no problem with that. We don't just have to store the simple state. So that's a quick look at things. There's a lot of resources here. If you want, I can share the slides later to help you get started on this or look at these extra things. If there's any time for questions, I'm happy to answer any questions. You have some time? Yep.
I just have one. You said that you save the event before the command actually succeeds or fails. So that kind of means that you can't really reproduce your data set away reliably the way it was, because maybe if the event, if you report the event and the command fails.
No, you check the command passes first of all. You validate the command.
Yeah.
Is the command a good command?
Yes.
Validate it, check, then you save the event.
What if it's timeout?
If the actual operation fails, then we try it again. Okay, later we can rebuild the system and try it again. We have this event stored.
Okay, so you do that infinitely?
Well, then there's problems there. But if the system's not running and not working, we have a bigger problem, I think, than if you can't finish the processing.
Conflict management, stuff like that?
Possibly, but I think we have a bigger problem if we can't process the event in time. It's timing out all the time. So the validation is very important, like checking the bank balance. Do we have enough money in the bank to actually perform this? If we do, then we can just write that event out. You validate it before you save it. It's sort of the opposite way around you'd think. You'd think you do the command first of all and then say, oh yeah, it worked okay. You check, will it work, first of all. Okay? Any other questions? If not, thank you very much for your attendance. And